We started chapter 7 talking about area. We know that if we think of a region as infinitely thin rectangles that we add from one boundary to the next, we can find the area of a full region. And then we moved on to this method where we rotated one function around the x-axis. We used the integral notation to add areas of these thinly sliced circular disks to find the volume of a three-dimensional curved objects, or three-dimensional curved object, like what we did with the previous lesson. But what if we were asked to find the volume created by rotating that region between two functions? So take a look at the region that we have here below. You got the y equals x squared parabola, and then we have y equals square root of x, which is the radical function. And picture that region that is enclosed by the two graphs, kind of a leaf that is pointed at a kind of an angle, a 45-degree angle there. So picture taking that region and rotating that shape 360 degrees around the x-axis. Right. So there's still a circular based object, right? We know it's going to be a three-dimensional object. But what shape do you see? What difference is, do you see any distinctive difference between this object that's created versus the object that was created with just one function rotated about the x-axis? Okay. So still circles involved, but one distinct difference is the fact that there is, because of a gap between the axis of revolution and the shaded region, that gap is going to kind of take effect in the sense that the object that's created is going to be hollowed out. It's going to be a bowl, or it's going to be a ring-like shape. It's not going to be a full compact solid that we saw with the circular disc creating these objects from this method. So as we rotate this kind of a leaf shaped two-dimensional region around the x-axis, you can kind of visualize it creating these circular rings. Okay, so imagine taking these, imagine slicing this bowl-shaped object into really thin slices. Instead of getting circular discs, you're going to come across with these circular rings, or we call these washers. Okay. So here's another picture of that representation. Imagine taking this bowl-shaped object and just taking one slice of it, and any slice that you pick, technically there's a hole here, we just don't see it. Any slice that you pick, there are going to be these circular rings with various outer radius and an inner hole or inner radius. So here's a representative cross-section that we would create if we were to cut, or if we were to separate this bowl into thinly sliced regions. Basically going to be a circle within a circle, like a donut-shaped or a ring-shaped area. Now, if I asked you what the area of a circle was, you would just say pi r squared, right? It would be pi r squared. But what if it was a ring-shaped object with the center, circular center that's cut out? If we were to find the area of this shaded region, you would still involve area of a circle, but area of one circle is not going to be enough, right? We have to think of it as the area of the large circle minus the area of the small circle. Okay. And that is going to be something that we're going to be using that's distinctly different from this method. With washer method, we have to think of it as subtracting out the inner circle from the larger circle. With this method, we only had one radius to deal with since there was no hole, there's no gap to subtract out. But now that there's a hole, we have to think about finding that dimension for that inner circle. Otherwise, we won't be able to get that calculation that we need. So back to this leaf-shaped region that we're dealing with. As we rotate this, we're going to have a certain outer radius that's going to be created from this object. And there's also a certain inner radius that we're going to have to subtract out. So the way we find the outer radius is we're going to extend from the axis of revolution to the further boundary. So this is represented by the outer ring, that distance from the center to that outer ring. And then little radius is going to take up that distance from the radius to the closer of the two boundaries. And that little r is going to represent the radius of the hole that we're going to subtract out. So each slice has the shape of a washer, the circular donut, and the area is going to be equal to area of a big circle minus the area of a small circle. So if we were to adapt this into pi big R squared minus pi little r squared, we're going to take this area calculation and we're going to give it a certain width, and that width is going to be a dx, just like how we did with this method. And once we give that area, this ring-shaped area calculation, we're going to give it that dx, that width component, and then finally the integral notation that will accumulate all these different size rings from one end of the object to the other. Just like how we use the integral notation to add up infinite numbers of rectangles for area, and just like how we added up infinite disks for the disk method from one end to the next, now we're adding infinite numbers of these circular rings or these washers from one end to the next with a slightly adjusted formula that accounts for the hole that we want to subtract out. Okay, let's look at a few examples on the next page. So here are the steps that we're going to take on. First thing is confirm that a gap exists between the axis of revolution and the shaded region. So one thing I want you to take notice of is we're going to go back to this example that we used to demonstrate on that previous page. And look at that distinction between this method versus washer method. One thing that is really noticeable is the relationship between the axis of revolution and the shaded region. Notice that with this method, there's not going to be any gap between the dotted line and the shaded region. See how the shaded region is flush right up against that axis. There's no gap, there's no hole, there's no curved region. So basically, if there's a gap, or even if it's touching a part of a curved region, that is going to be a giveaway that there's going to be a hole, there's going to be a gap, there's some sort of an indentation that's going to be created. And because of that, we always have to use washer method. So this method, you can tell if your axis is up against a flat surface, then all we need is one radius. But if your axis and the shaded region has any sort of a separation, even if there is a portion that's touching, if there's any sort of separation, any sort of a gap, we have to account for the fact that there's a hole, there's a divot, there's some sort of a portion that we need to account for with that inner radius. So the first thing we're going to do, so we confirm that there's a gap. For this problem, it says it's revolved about the x-axis. So that is where we draw our dotted line. That's going to be where our axis of revolution is. That's going to be the center. This is the center of this bowl, of this object that we're going to create. And because we know that there's a gap, we know this is washer method, we know that there's going to be two distinct radius that we have to draw. So the first thing is we're going to draw a big radius. So big radius is going to extend from the center, or the dotted line, the axis of revolution, and we're going to go all the way to the furthest boundary of our shaded region. So there's our axis of revolution. There's the center of our axis of revolution. We're going to extend all the way to the outer boundary of our shaded region. Basically, the boundary that's furthest away, that's going to create a longer length. So that's big R. We'll call that big radius. Next thing, we're going to place our pen or pencil on the dotted line again. And now we're going to extend to the closer of the two boundaries. And the closer of the two boundaries is going to be a shorter length, and that's going to extend to this x squared graph. So we have our big radius, we have our little radius. Just like with this method, just like with area, we're going to do top minus bottom, but now we got to do it for both big R and little r. So big R is going to be top graph of root x minus, you see the bottom, the radius is on the 0, so it's root x minus 0, top minus bottom. For little r, we also have a top and bottom of this radius length. The top of the radius is sitting on the x squared. The bottom of the little radius is sitting on the 0. So x squared minus 0, that's going to be our little radius. And now we simply plug it into our formula. Our bound, we still have the pi involved. They're still circle related, so that pi will be there. Our bound is from 0 to 1. That's the furthest left of our shaded region, and the furthest right x value of our shaded region, which is 1. Big radius quantity squared minus little radius quantity squared. So we put everything that's part of big radius into that expression of big radius, and we square the entire expression, minus, and little radius, put it into that space here, and then we square that as well. So we get square root of x quantity squared minus x squared quantity squared. These two expressions clean up to be just x minus x to the fourth. We can enter that in the calculator. Math 9 for TI-84 or 36 Pro with a second E. Get that notation to show up. Integral from 0 to 1. X minus x to the fourth dx. Leave the pi out of the calculator. The calculator will produce 0.3, or you can do fraction to get to 3/10, and then you're just going to fill in that pi yourself. Just write that in. Okay, example 2. Find the volume of the solid bounded by y equals x squared plus 1. That's this parabola here. Y equals 2. That's this line here. And we're revolving about the x-axis. Now look at the shaded region in relation to the axis. Notice that there's a huge gap. All right, actually it's a complete hole. So it doesn't matter if it's a hole or a gap. Any of these situations we're going to have to use washer method. Notice again how this is very different than anything with this method. Right? With this method, your axis of revolution is always going to be up against the flat surface of your shaded region. You're not going to see any gaps, any separation between your axis and your shaded region. If there's a complete separation or a relatively small separation, any separation is going to require us to use this washer method. So in this case, we're going to have to actually find the bounds. The bounds are not visible to us like the previous problem. So the way we find bounds is the way that we did with area with 7.1. we set our two equations equal to each other, and we solve for x. Okay. We set our equations equal to each other. We get x squared plus 1 is equal to 2. We solve for x. We bring everything over to one side. We get the 0 to show up on the right side. We can continue factoring. We get x squared minus 1 expands to be x minus, or factors to be x minus 1, x plus 1. We solve for x, and we get 1 and negative 1. So those are the bounds that we're going to be using for our volume formula. Our next thing is we know we have to draw two radius because we have a complete gap, and that gap requires us to have to use two radius. There's a big radius that's going to, again, you always start on the axis and you connect to the further boundary. You never want to connect that distance between the two curves. The reason why is because we're calling it the radius. If we're calling it the radius, the center of our object has to be involved for our radius. So always follow the directions here. You're always going to place your pen or pencil on the dotted line, and from the dotted line you're going to extend to the boundary of your shaded region. In this case, we're going to draw up to our boundary of our shaded region. It's going to go all the way to that y equals 2 line. And then little radius will extend from the center, this is the object, this axis of revolution, to the closer of the two boundaries, which is the x squared plus 1. So now we're ready to find the representative lengths of the two radius. So big radius is top minus bottom. The top of the big radius is sitting on the y equals 2, this horizontal line. The bottom is sitting on the 0, so we simply say 2 minus 0, top minus bottom. And that's just going to give us big radius. For little radius, the top of the little radius is sitting on the parabola, which is the x squared plus 1, so that's the top graph, minus the bottom graph, which is the 0. So x squared plus 1 minus 0 is just x squared plus 1. Okay. Once we have that in place, then we're ready to put into our volume formula for Washer method, which is pi big radius squared minus little radius squared. Big R squared minus little radius squared. So our big radius is 2, so that goes into that big R component of our Washer method. And then the x squared plus 1 is the little radius. That's going to go in the little r component of our volume formula. We have our bounds from -1 to 1, and the rest can go in our calculator. Again, leave the pi out of your calculator. The calculation will give you 64 over 15 after you convert that decimal to a fraction, and then just add that pi into the answer with units cubed to represent we're dealing with a volume dimension.